Hello there. In section 3.2, we are going to learn more about functions. We are going to start with reviewing some terms you would have heard in an algebra class previously. Those terms are going to be domain and range. And what the domain and range is, the domain refers to the set of all of our x values in a function. So the domain is the set of all the x values. We also call these the input values. It's all the numbers that we put into a function. The range is going to be the set of all the y values. These are also called the output values. These are the values that we get out of the function. So if we think back to what we did last class, when we evaluated something for f of x, maybe it's x squared minus 4, whatever we put into the x would be the input value, or those values would be in the domain. Whatever we got back as f of x would be a range value, or the output values. Okay, let's keep going. So we need to review a couple things first. So what kind of values can we never have under a square root? Right, that would be anything that's negative. We do not want any negative values under a square root. So if we consider this expression here, the square root of x plus 4, what values of x would result with real numbers? So what numbers would be okay to use for x? Well, if we use a value of 0, what's 0 plus 4? 4. So that would work. What about if we use 5? 5 plus 4 is 9. The square root of 9, that's okay. So we could keep guessing. Even if we use negative 2, negative 2 plus 4 is 2, which is still okay. However, that could be cumbersome to guess all of the values that would be okay. So what we can do is we take the radicand, which is the expression under the square root, this x plus 4. And we need that to be greater than or equal to 0 because we just want it to not be negative. So now if we solve this inequality for x, and to do so we know that we just need to subtract a 4 from each side, and we're left with x is greater than or equal to negative 4. This tells us what values would produce real numbers. So as long as our value of x right here is greater than or equal to negative 4, it would produce a real number. And we can check that. For example, if we have the square root of negative 4 plus 4, well, this would be the square root of negative 4 plus 4 is 0. The square root of 0 is just a 0. So we know that works. So something bigger than negative 4, we already talked about this, but if we try another one, let's say a negative 1. If we have negative 1 plus 4, well, negative 1 plus 4 is the square root of 3, and well, 3 is not a perfect square, but we could evaluate the square root of 3, and we're getting approximately 1.7, and it continues on from there, which is also positive, so we know that works. So that tells us that every value of x that's greater than or equal to negative 4 would produce a real number. So that one was pretty easy because we can visualize it. But what about in the expression 3x over 2 plus 4? Now you might not be able to think what values of x here would make this to be greater than or equal to 0. So this is where we have to use this approach. So what I want you to do is take this expression, the radicand, let it be greater than or equal to 0, and solve for x to find which values would result with real numbers. So go ahead, pause the video, and work through that. Okay, so first thing we do is we take the radicand and we let it be greater than or equal to 0 because we need it to just not be negative, which means it could be 0 or bigger. And first thing I did is I subtracted a 4, and then I cleared my fractions. You could have cleared your fractions from the beginning. It doesn't matter which order you do that. So my 2's here would simplify out, and we get 3x is greater than or equal to negative 8. Divide both sides by 3, so we get x is greater than or equal to a negative 8/3. So as long as we use a value that's at least a negative 8/3, and then we could say or larger, then this expression would result with a real number. We need to use this method in order to find the domain when we have a function that has a radical in it. And we'll look at all those examples on the next page. The other thing we need to review here is what number can we never have as a denominator. So for example, if we have 18 over something, what value can we not have in a denominator? Right, we cannot have a 0 as a denominator because 18 over 0, this would be undefined. So we do not want a denominator of 0. So we can say here, therefore, we know in the expression 1 over x, x cannot be 0. We just talked about that over here. But we want to consider this expression, 1 over 4 minus x. What value of x would make this expression undefined? Well, we don't want to just be quick to say, ooh, 0, because if we have 1 over 4 minus 0, what's 4 minus 0? Well, that's just 4. So that's actually equal to a 1/4, which is absolutely okay. So in this case, what value could we substitute in here that would cause this expression to be equal to 0? This one's pretty easy. You could look at it. 4 minus what? Right, that would be 4. Now, if we wanted to solve this, we could set this denominator equal to 0, add our x to both sides, and when we say, okay, 4 is equal to x, that means when x is equal to 4, this denominator would be undefined. So what value would make it undefined? That would be the value of 4. Now, just like in the previous examples, this one's easy to look at, but what if we have something a little bit more difficult like this? What value of x would make 1 over 4 minus 3x undefined? So what we want to do is take that denominator, and we want to know, when is this expression equal to 0? Now we have to solve that for x. So now I want you to pause the video and solve for x. So to solve this, one of two methods, you can either add the x to both sides like I did here, or you could have subtracted a 4. Either one is fine, you'd get the same answer. And then I divided by a 3, so I get 4/3 equals x, or I can always rewrite that as x equals 4/3. So what value of x would make this expression undefined? And that would be the value of 4/3. So here, any value of x would be okay except for 4/3. Anytime we are faced with a function that has a variable in the denominator, this is the process we have to keep in mind because we don't want that denominator to ever be undefined. Okay, so now using what we remember from denominators and square roots, let's go ahead and find the domain of some functions. So example 1, we want to find the domain for the given functions. Before we get to it, let's look at them. In problem A, we have f of s equals the square root of s minus 2. So we want to think, okay, we have a radical. What do we know about radicals? They cannot be negative. So here we have to take this expression, the radicand of s minus 2, and we need that to be greater than or equal to 0, because we remember that a square root can't be negative. That's what we need to remember. And then when we look at example B, okay, we don't have any radicals. We have f of n equals n squared over 6 minus 2n. We are not concerned with this numerator. We just want to focus about the denominator. What do we remember about denominators? We know that denominators can't be equal to 0. So what we have to do is we have to find, if we have the expression 6 minus 2n, what value of n would cause this to be equal to 0. So now what I'd like you to do is go ahead and solve these, this inequality in this equation to find what values that we need to be working with. So go ahead, pause the video, and calculate those. So now when we solve the first one, we just need to add a 2 to both sides so we get s is greater than or equal to 2. So now what we want to do, since we're trying to find the domain now of a function, we need to add a little bit more to this answer. What we want to say is all real numbers where s is greater than or equal to 2, this would be the domain of this function, meaning we can use any value, in this case of s, that's greater than or equal to 2. We say all real numbers because they could be rational, they could be irrational, we could have whole numbers or integers, we could have decimals, fractions, any of them, as long as that value of s is greater than or equal to 2, those values would be in the domain of this function. Because if we use a value smaller than 2, this function would not be a real number, so that would not be on the graph. Now, looking at letter B, we found that the value of 3, if we substitute in a 3 here, 2 times 3 is 6, 6 minus 6, the value of 3 would cause this denominator to be undefined. So the way we have to write this answer is we can say all real numbers except n equals 3. So that means that we can use any value of x, or in this case, the input value of n of 3, we can use any value of 3 that would be in this domain. So that means if we were to graph this, every value of x would be in this domain except for 3. Now, if you don't want to write out all real numbers every time, you can always use the symbol that looks like this. It's like an R with 2 vertical lines. This also works if you don't want to write all real numbers. Okay. Now let's go ahead and look at an application problem. A formula used to determine the number n of board feet of lumber that can be cut from a 4-foot section of log of diameter d in inches is, and we are being given this formula right here. I'm just going to highlight it for now. It tells us asks us what are the domain and range for the function for values of d from 10 to 40. These would be our input values because it wants us to put these values of d into this function to calculate our n. Therefore, our input values are our domain values. So we don't even have to do any work to calculate our domain because it tells us right there. So our domain values are going to be all values from 10 all the way up to 40. Now what we want to do is write this using an inequality. So we can say all the values we want to find of, not n, but d. D has to be greater than or equal to 10, but we also need d to be less than or equal to 40. We're not concerned with the diameters that are smaller than 10 inches, and we're not concerned with the diameters that are larger than 40. So this is our domain. Now this problem is also asking us to calculate our range values, meaning when we put these values in, what values are we getting out? So how do we do this? Right, we have to substitute in the domain. Now, you don't have to substitute every numbers between 10 and 40. We just need to find the biggest and the smallest. So we just need to simply substitute in the 10 and the 40 to find our smallest and our largest. So we can say n is equal to 0.22, but instead of d, we want to use the smallest diameter of 10 and square it, minus 0.7 times that smallest diameter. And then we can use our calculator to help us. So we put 0.22 times 10 squared minus 0.7 times 10. And when we calculate that, we're finding an n value of 15. And this would be 15 feet because that's what we're talking about for n. So that is the smallest range value that we will get, meaning that's the smallest output. So now we can start by putting our 15 here. Now we need to calculate our largest range value. So I want you to go ahead and evaluate this function for the diameter of 40 and then finish writing our range. So pause the video and go ahead. Okay, so when we calculate the input value of 40, and I just typed this into my calculator, I'm getting an n value of 324. So that's the largest output we can receive with the largest domain value. So that means our range consists of all values of n between 15 and 324. So 15 is less than or equal to n, which is less than or equal to 324. And for the last example here, we want to evaluate the indicated function. Now notice how h of s is equal to two different pieces. We want to evaluate 2 of s for values of s less than -1, and we want to evaluate s plus 1 for the values of s greater than or equal to -1. We call this a piecewise function, meaning there's two different pieces to this graph or this function. So for the first one, we want to evaluate h of -8, but we need to determine which piece of the function do we have to use. So we have to take this -8 and determine whether it makes this true or whether it makes this true. And -8 is less than -1, so we evaluate h of -8 into this function. So we'd write this as h of -8, and that's equal to 2 times -8. Well, we know 2 times -8 is -16, so that tells us h of -8 is -16. Now for the other part of this, we have to evaluate h of 2. So again, we have to go up to the function and figure out which one of these is true for the value of 2. Well, 2 is not less than -1, 2 is greater than or equal to -1, so we evaluate 2 in this piece of the function s plus 1. So this, instead of s plus 1, we input 2 plus 1. 2 plus 1 is 3, so therefore h of 2, h of 2 is equal to 3. Okay, that's all we have to do for 3.2. So give the lab a try, the homework a try, and let me know if you have any questions.